All right, so we are going to take a look at ions. So how do we draw the dot structure for an ion? What does it change about our method? And exceptions to our octet rule. So we're going to do both of those things. So these first ones are drawing our Lewis dot structures for those polyatomic ions we so love in our ionic bonding. So we're going to see how they are actually bonded to each other. And this is in the covalent bonding sections because that's what holds these polyatomic ions together. These covalent bonds, they share electrons. So when we want to draw a dot structure, the first thing we have to do is add up the total number of electrons that we have, our valence electrons. So we need to add them up for all of these elements here. So how many valence electrons does nitrogen have? 5. All right. So you have to vote for 5. How many does hydrogen have? 1. But there's 4 hydrogens. So that gives us 4 valence electrons. So we would have a total of 9 valence electrons coming from our elements there. However, it has a positive charge. What does a positive charge tell us? An electron is missing. We've lost one of our electrons. So we're going to go ahead and subtract 1 from that total. Okay, we lose an electron to become more positive. Lose the negative, become positive. So that means to draw this structure, we have 8 electrons. We need to use all 8 of them. So we would put our atom that's going to go in the middle. Typically, it's your first element that's listed. So we're going to put that in the middle and then surround it by our other atoms. So we've got 4 hydrogens. We're going to place the 4 hydrogens around it. And then for those of you who have gotten to those notes, what kind of bond do we put between them? Single bond. We always start with a single bond. We only get to doubles or triples if we absolutely need it as a last resort. They're more rare. So with each line that we draw, we've used 2 electrons in a bond. So that means we've used how many electrons? 8. So we've used all 8 of our electrons. We've run out, which is good. Our hydrogens are happy with just 1 single bond. Our nitrogen in the middle has 8 electrons around it, which means it has its octet, has its set of 8, which everybody loves. So everybody's happy in this. Now the last piece to these ones that we need to show is that this thing has more or less electrons than you would expect it to have. It has a charge to it. So the way we do that is we put it in brackets, and then we show the charge on the outside. So we say, hey, this thing right here has a positive charge. It has lost an electron. So if you're adding up the electrons, you should know there's 1 less than you would expect. We need to indicate that.
Well, actually, once is a real instance of what's missing nitrogen for making 4 bonds.
Say that again?
Because the last thing you want to see is 4 bonds on nitrogen.
I mean, it can bond 4 times. It just has to kind of be forced into doing it by changing its charge. So it happens. Not often, but it does happen. All right, let's check out one more of these, and you can try one maybe on your own. So our sulfate ion, SO4 2-. Do we know how many electrons sulfur gets? How many valence electrons? 6. So we base this off our groups. That's how they get their charges, all of that. All right, and then we have 4 oxygen atoms. And how many electrons, valence electrons, does oxygen have? Has 6. All right, so what would our total be here? $30. All right, we have 30 electrons, but then we have a 2- charge. What does that tell us? Do we gain or lose electrons? Good, we gain electrons, so we need to add 2 more to our total, and we get 32 to play with. That's a lot more electrons than our last one. All right, so our steps still follow the same pattern. We're going to place our central atom. Again, typically it's our first element. We're going to surround it by our 4 others. We have 4 oxygens, so it's nice and symmetrical. And how are we going to bond them? Single bond. We're going to put a bond between each one. All right. Now, how many electrons have we used with those 4 bonds? We've used 8. So how many do we have left? 24. All right. So we have 24 electrons left. We still have to use up these electrons. So we start adding them onto our molecule as lone pairs, the dots on our outside atoms. Because these outside atoms want their octet. They still want their 8. Hydrogen's one of our exceptions. It doesn't care. It doesn't need an octet. It fills up its orbital with just 2 electrons because it's that first energy level. All right, so our oxygens, if I add 3 more lone pairs on one of these oxygens, it will get an octet. It'll have 2 from the bond and then 6 more, and that gives it its 8. So that gives us 6 there. 6 there is 12. This gives us 18. And this gives us 24. So we have now used all of our electrons. Go team. Yeah, it's way better than drawing them online. This with is the worst. I'm sorry for that torture. But you made it. All right. So what's the last thing we should do now that everything has its octet? We've used up all our electrons. Brackets and some 2- charge. Oops. All right. We feel okay with those? Yeah? So you got a third one there you could try out. Same type of process, nothing crazy there. Let's take a look at these ones at the bottom, these exceptions to the rule, because we love rules in chemistry, but we like to also break them. It's our thing we do. So we have some elements on our periodic table that don't need an octet. They don't need 8 electrons. Hydrogen over here is one of them. It only needs 2 electrons to fill up its orbital. It's nice and happy, so it gets one little bond. We're good. The other one that we'll deal with is this boron atom. Boron is a metalloid. It's already not following the rules. It's kind of wavering between metal and non-metal, and it only has 3 valence electrons. So it only really wants to bond 3 times most of the time. It can get an octet, but a lot of times it's only going to have 6 electrons around it. And that's perfectly fine for boron, we've discovered. So if we wanted to draw this, boron has 3 valence electrons. Each hydrogen has 1. So we have a total of how many from hydrogen? 3. So we get 6 electrons to play with. We don't have an octet to even start with. So kind of makes these ones a little bit different. We still place that boron in the center. Hydrogens always go on the outside, so we can surround it by the hydrogens. Doesn't matter what side we put them on. And then how should we bond them together? What should we put? Single bond. And each of those bonds represents how many electrons? 2. So we've used all 6, and we are done, and this is nice and happy. Right? So exceptions to rule, boron has less than an octet. And we just accept it. It's just part of what boron does. Now the weirder ones, in my opinion, are the ones that can have more than an octet. So why can they do that? Well, hanging out over here, starting in period 3, we get things like phosphorus, sulfur, chlorine, moving down after that. We have, in period 3, their valence electrons are in their s orbital and their p orbital. 3s, 3p. There is a 3d orbital, though, available and empty, ready to accept more electrons. So because of that, these atoms can expand their octet and accept and bond with more atoms and have more than an octet around them. But the process for drawing these isn't that crazy, okay? It's still pretty straightforward. So we're still going to add up our total number of electrons. Yes?
Is it wise polyatomic ions are possible?
Is what?
Is it why polyatomic? Is that
why?
Would that be why polyatomic atoms such as sulfate?
Yeah, that's part of it too, and just how they share their electrons. Yeah. So sulfur has 6 valence electrons, and we have 6 fluorines with how many valence electrons does fluorine have? 7? I thought I heard that out there. All right, so 6 times 7 gives us what? 32, and right? No, 42. Wow, I can do math today. No, I can't. All right. So we have 42 and 6 gives us 48. I'm awake. Promise. I just need to keep drinking the coffee. All right. So we have 48 electrons. This is a lot of electrons to deal with. Okay. We're going to stick our sulfur in the middle, and we're going to go ahead and bond all 6 of these sulfurs to, oh my gosh, of these fluorines to the sulfur. I can think today, guys. I really can, I swear. So I'm going to go ahead and put my bonds there just because it helps me organize it and get all these fluorines to fit. This is true. So that's 42 and 6 is 48, right? Okay. Oh my gosh. Because 6 times 8 is 48. Because it rhymes. All right. So this gives us this like Ferris wheel of sulfur and fluorine. How many electrons have we used at this point? 12. So we have 36 left. Okay, if we look at our fluorines, they each have a bond, so they need how many more electrons? They need 6 more. So if we add 6 electrons to these 6 atoms, 6 times 6 gives us 36. So that will use up the rest of our electrons. So they all get 3 lone pairs of electrons. We add all our cute little dots in there. It's crowded, but it works. Make sure as you draw these two that your lone pairs look like a pair, not just a random grouping of dots around an atom. All right, we do want to make them look like pairs. So that would use up all 36 of our electrons. And sulfur's fine with this because, again, it's adding those extra electrons that it's bonding to into its d orbital, so it's able to make those extra bonds. Okay. Our others over here would be very similar. PCl5, very, very similar to this one. But let's jump to the last one because I think it's extra fun. And it bonds xenon. What's weird about bonding xenon?
It shouldn't be bonding to anything. It's a noble gas.
It's a noble gas. You've been told in all of your chemistry that noble gases don't bond. They don't bond. Yes, they do sometimes when we force them to in a lab. All right. So they don't bond that often. Let's put it that way. All right, so xenon has 8 valence electrons. We got 4 fluorines, each with 7 valence electrons. So we have 28 plus 30, or plus 8 is 36. I can do math today, sometimes. All right, we're gonna go ahead and put our xenon in the middle. And we can put our fluorines around it. We only have 4 fluorines, so that's nice and normal. Bonding 4 atoms to a central atom. We add that single bond in. Oh, that's just a really long single bond now. Where's my whiteout? Let me fix that. Or not, because my whiteout's gonna die. Okay, one really long bond. Okay, so to finish out our fluorines, we need to add some lone pairs, give them their dots to finish out their octet. We got plenty of electrons to do that. All right, so around each of our fluorines is 8 electrons, including that bond. So we've got 8, 16, 24, 32 that we have used. We have 4 electrons left. When we get to this point when we have extra electrons, in the steps to draw these, it says place extra electrons on your central atom. Okay, well, our central atom is xenon, and we're going to place them as a lone pair on xenon. So this is where it starts to get weird, and we get extra electrons. We get more than that octet on a xenon. And we do it by adding some lone pairs. They go kind of in between the bonds where you can find some space to put those lone pairs in. Okay, and that finishes out xenon tetrafluoride is what we call that. So that uses up the rest of our electrons. So these are just some of the kind of different ones, having things with charges, having some exceptions to the rule. You can try out the PCl5, the PO4, 3- phosphate ion as a little extra practice. So now everybody's seen some of these. I believe that, make sure when you're looking at these, there were a couple of typos in the packet. I think I caught them all for everybody, but if you got your packet pretty early, make sure I checked it. A couple of these should have negative signs on them, that kind of thing. I got through most of them. So